Now, in 3 dimensions, these curves are going to be down in the xy plane, and they're going to intersect at the origin. I'll draw them in green just like I did here. They're going to intersect at the origin and at the point 1, 1. So I sketch those 2 points, and then I draw my curves. Well, one of the curves is really straight. That's the y equals x line. So the y equals x line just goes through these 2 points. So here's y equals x. And then I have the y equals x squared, which stays closer to the x-axis, but then gradually curves up and goes through the point 1, 1. Well, it's going to stay closer to the x-axis and curve up here, so it's going to look like this. And now, here's our region. Well, what we're integrating is x squared times y squared. So, and this is consistent with what we've seen previously, and let me get a good color to do this in. Orange or purple? I'll go with purple. Okay. What's the value? We're going to do the graph of x squared y squared above this region. Okay? Because what this integral is going to give us is the area above this region and underneath the graph of the x squared y squared surface. Well, the x squared y squared function, but the surface defined by that graph. Well, if x is 0, well, if x and y are both 0, then z equals x squared y squared is going to be 0, right? So we're looking at z equals x squared y squared. Okay? Now, if x and y are both 1, which occurs at this point, then what's the value of z going to be? Well, it's going to be 1 squared times 1 squared. It's going to be 1, right? So at this point, okay, well, let's label the points. 0, 0, 0 is on the graph, and the point 1, 1, 1 is on the graph. Okay? And this is 1, 1, 1. I mean, this does represent 1, 1, 1 because it's here's 1, 1, and here's a distance that seems to be about equal to 1, right? Okay? Now, again, it's going to be a little clumsy trying to draw this because we really need to rotate everything 180 degrees and look at it from the back. But if we do, then we don't see the front. So, yeah, we kind of messed up either way. Okay, well, along the line y equals x, graph is just z equals x to the 4th. Okay? Now, depending on how familiar you are with graphs of power functions, the characteristic of x to the 4th is a z equals x to the 4th graph would look just like a z equals x squared graph, but it would be much flatter. So, if this is the point 1, 1 in the zx plane, the x squared graph goes through 1/2, 1/4, and it's flat here. So that would be the z equals x squared graph. if x equals 1/2, x to the fourth is 1/16. So the x to the fourth graph would only be a fourth as high here, but it goes all the way up to here. So it's much, much flatter, and then all of a sudden gets much steeper. Now this is something that people are supposed to learn in pre-calculus when they study functions. I'm afraid that what often happens in pre-calculus, you just put a calculator in people's hands, never ask them to construct these graphs. Okay? So nobody really understands this except if you punch it in a calculator and look at it. Okay? So I'm simply saying you're very adept at this sort of thing. That's the sort of thing that's a good thing to think about. It gives you a better feel for what happens here. It's just basically then along this line in the plane above this line here, the graph stays very close to the line and then suddenly goes up very steeply. Okay? Maybe something like this, and then I can kind of shade this to show where that is. Okay? Now, along this line, your y values are smaller than they are along this line. Along this curve, the y values are all smaller than they are here. So when you square them, they're much smaller. So along this curve, the graph pretty much stays very close to the curve until you get out pretty close to here, and then it goes way up and fast. So above this curve here, it looks something like this. Okay? Now, we could do all kinds of analysis and figure out what it looks like between here and here. Okay? But it's going to do something much like this. So it's kind of a fancy shell evolved by some creature. Okay? Now, what's the volume of that shell? Above the xy plane, right? We can estimate that the volume is pretty small. Okay? I haven't looked at what you got for the integral, I looked at the process. Didn't pay that much attention to the final result. But I can say this. If I was to draw a unit cube here, it would have a volume of 1, right? Now compared to the volume of this whole cube, the volume of that little seashell or whatever it is, very weirdly shaped, but you probably find something in the ocean that has a similar shape because you get all kinds of stuff, okay? And which incidentally is very interesting to model mathematically and informs us about the nature of the creature that builds it by mathematical analysis. Okay, one aspect of this that just occurred to me that would apply to your field, okay? So, I would say that certainly the volume of what's in here is less than 1/10 of the total volume, okay? And I think quite a bit less than that. I'm guessing between 1/30th and 1/10th, which would be between 0.03 and 0.1, okay? So let's see what you got for your integral.
I think